Good morning, good afternoon, or good evening, and welcome to my talk on the European Environment for Scientific Software Installations, or EESSI for short. Before I get started, I would like to thank the organizers of the HPC Knowledge Meeting to continue with this event in an online format and for accepting my talk proposal. Let me get started by quickly introducing myself. My name is Kenneth Hoste, and I have been working in the HPC team at Ghent University in Belgium for the last 10 years already. Time flies when you're having fun. I mainly focus on user support and software installations, and over the years I have become the lead developer of the EasyBuild project, which you may have heard about already. There's a lot of things I like, including a nice cold beer and open source software, but there's also a whole bunch of things I don't like, which are relevant in the context of this talk. Here's the outline of this talk. I will introduce you to the EasyBuild project, explain what we do, who is involved, and why we are doing this. I'll briefly cover the history of the project and talk about the scope and goals we have. We'll take a look at how the project is structured and how we plan to achieve the goals we have in mind, and which opportunities and challenges this brings. At the end of the talk, I'll give an overview of what we have done so far, and I'll try to motivate you to collaborate with us. Let's set the stage by briefly looking at how scientific software is or should be installed in an HPC context. We typically compile scientific software from source, so we can optimize the installations for the specific system on which they will be used. Things get messy very fast, however, even without taking the performance aspect into account. To get a scientific application installed, you may have to install a whole bunch of dependencies first, or you may have to deal with a large complex codebase, which is maybe not well maintained or poorly documented. And you'll have to use very recent compilers that can do a good job in building binaries for those shiny expensive CPUs you have. In my experience, this situation has been getting worse in recent years, for a number of reasons. I'll get back to that in a bit. I will introduce you to the European Environment for Scientific Software Installations, or just EESSI for short, EESSI. The EESSI project is a collaboration between different European partners in the HPC community to build a common scientific software stack for HPC systems and beyond, including personal workstations, laptops, and cloud infrastructure. The concept is heavily inspired by the Compute Canada software stack, which I'll briefly talk about. It is a grassroots project, by which I mean that it was created by a bunch of technical people who wanted to collaborate on something useful and try to do a better job at installing scientific software, which is something they haven't been able to do well due to a sheer lack of time. It is also a good excuse to have beers together. Here's an overview of the current partners in the EESSI project. It was started by a bunch of Dutch universities together with Dell Technologies and the University of Cambridge. Later, additional partners were added, including myself, representing Ghent University, the Jülich Supercomputer Center, the University of Oslo, the SURF National Institute in the Netherlands, and the HPC Now consultancy company who is organizing this HPC Knowledge Meeting. The motivation for this project is the changes we see in the HPC community. First of all, there is an explosion in the number of different scientific software applications that are used on HPC platforms. A big part of that is happening in bioinformatics, machine learning and AI, deep learning, and so on. We also see more and more researchers making their code available to others, since there is an increase in pressure for publishing code together with research articles. HPC is also being adopted more widely across scientific domains. See, for example, the recent interest in GPUs in bioinformatics. Next to this, there is a clear trend towards also using cloud infrastructure for scientific calculations. And on top of that, there is way more variation in CPU architectures today than there was in recent years. Not only is AMD back in the game next to Intel, but there's also increased adoption of ARM processors for HPC calculations, and power is still around as well. In the near future, we may even see RISC-V-based processors through the European Processor Initiative, for example. And then we're not even mentioning different GPU vendors and other accelerators. In contrast, the manpower that is available in HPC support teams for helping out researchers with installing the software they need remains limited in many HPC sites. The idea for the EESSI project grew after several Dutch universities visited the University of Cambridge by invitation of Dell. They wanted to work together on something useful, and they quickly came to setting up a shared software stack on top of CVMFS. Several of these sites were already using EasyBuild for maintaining their local software stack. It didn't take very long before they discovered the work that was done by Compute Canada on their central software stack. through a talk that was given at the PERC conference in the summer of 2019. Via Dell, I was invited to join the next project meeting in Delft to see if we can work together on this. Since then, we have been organizing monthly meetings online to try and get ourselves organized. As I already mentioned, the idea behind this project is based on what Compute Canada did for their central software stack, which is used on all 5 major national systems in Canada, next to a bunch of smaller ones. The Compute Canada software stack consists of 3 layers, using CVMFS, Gentoo prefix, and EasyBuild and LMOD for the scientific software. For the middle layer, they were using Nix before, but they switched to Gentoo prefix because of problems that occurred when updating the middle layer. Maxime and his colleagues discussed the design of their software stack in the PERC paper, and it has also been presented at the EasyBuild user meeting. In addition, the detailed documentation provided by Compute Canada is openly available as well. Links to all of these resources are available in this slide. Here's a slide I stole from Maxime's presentation with his approval, of course. On the left, it shows how many software packages are included in their software stack, which is over 600. And if you take into account software versions, different CPU architectures, and compiler toolchains that were used to install this software, there are over 4,000 installations included in this software stack. The top graph in the middle shows how quickly the number of installations has grown over time. The green line on the top shows the total number of installations, and you can see a big bump there about halfway when software was rebuilt for Intel Skylake. The bottom graph in the middle shows the storage space that is required for all these installations, which is only about 600 gigabytes in total. The deduplication that CVMFS does is a big help here. Now let's take a look at what we have in mind for the EESSI project. We want to set up a shared repository of scientific software installations, and by doing so avoid lots of duplicate work across HPC sites. For end users, we want to provide a uniform user experience with respect to available scientific software, regardless of which system they use. We hope to make this work for any Linux distribution and maybe even Mac OS and Windows via WSL, and a wide variety of CPU architectures. Our software stack should work on laptops and personal workstations, HPC clusters, and in the cloud, which means we'll somehow need to support different CPUs, networks, GPUs, and so on. Of course, we want to focus on the performance of the software, but also on automating the workflow for maintaining the software stack, and thoroughly testing the installations, and also collaborating efficiently. Here's a high-level overview of the structure of the EESSI project, which is very similar to the Compute Canada software stack. The bottom layer in green is the Filesystem layer, which is responsible for distributing the software stack across clients. For this, we will use CVMFS. The middle layer is a compatibility layer, which ensures that the software stack is compatible with multiple different Linux distributions, and even Mac OS or the Windows subsystem for Linux, or WSL. The top layer contains the actual scientific software applications and their dependencies. Here we will use EasyBuild and LMOD together with Archspec. The host OS still provides a couple of things, like drivers for network and GPU, support for shared file systems like GPFS and Lustre, a resource manager like Slurm, and so on. Let's take a closer look at the file system layer first. Here we will use CVMFS, also known as CVMFS, which is a scalable, reliable, and low-maintenance software distribution service, as mentioned on our website. It's basically a distributed file system that is organized in different tiers. There's a Stratum 0, Stratum 1, proxies, and clients. It was created by CERN to distribute the software stack for the Large Hadron Collider project. It is a POSIX read-only file system, which can be mounted in user space using a Fuse kernel module. So CVMFS was built specifically for distributing software. So it handles lots of small files well, and it can deal with the access pattern that is observed when using software. The software is distributed through HTTP, and it uses aggressive caching to deliver good I/O performance. It has been shown to scale up to hundreds of millions of files and hundreds of thousands of clients. This is what the CVMFS hierarchy looks like. At the center, you have the Stratum 0. This is one server in the CVMFS hierarchy where the CVMFS repositories are hosted, and also where new software is being added into the file system. The access to the Stratum 0 is usually restricted through firewall rules for security reasons. The Stratum 1 servers are CVMFS replicas. They have a full copy of the repositories, and they're basically a read-only mirror of Stratum 0. There are multiple ones which are typically distributed geographically. They provide the software stack through a standard web server. The intention of the Stratum 1s is to reduce the load on Stratum 0 and to improve the reliability of the file system. Although clients can connect directly to a Stratum 1, this is not done typically. The squid proxies are reverse proxies for the Stratum 1 web servers. They are there for multiple reasons. When connected to a Stratum 1, they are mostly there for security reasons. For clients, they help to improve I/O performance by doing aggressive caching. They also help to reduce the load on Stratum 1 servers, and they can be used for load balancing. Clients typically connect with the software stack through one of these squid proxies. Finally, there's the CVMFS clients, who access the software stack usually through a squid proxy of a Stratum 1 server. Clients include laptops and personal workstations, but also HPC clusters and cloud instances where the software stack is available. Bigger setups like clusters or cloud instances usually have their own squid proxy for aggressive caching and improving I/O performance. But clients also have their own local file system cache. The key point here is that the same software stack is available no matter which client is being used. The middle layer of the EESSI project is the compatibility layer, which is where we use Gentoo prefix. It basically consists of a bunch of Gentoo Linux packages installed in a non-standard location, which is called a prefix. For this, we use Portage, the Gentoo package manager. Gentoo prefix supports a range of CPU architectures, including x86, ARM, and to some extent also Power, and it has support for both Linux and macOS clients. In the EESSI project, it is used to ensure the compatibility of the software stack with a different range of client operating systems, and we only use it for a limited set of low-level libraries and tools, including glibc. The top layer of the EESSI project is the software layer, which provides the actual scientific software installations. These are installed using EasyBuild and are optimized for a specific system architecture, a specific CPU, maybe also a GPU. For these installations, environment modules are provided so you can easily load the software and make it ready for use. The software in this layer leverages some of the tools and libraries in the compatibility layer, so it does not use anything from the host OS. Some things like kernel modules and drivers for network and GPU are still provided by the host OS, however. The best suited part of the software stack can be selected automatically for a given host. For this, we rely on Archspec. Let's take a closer look at the tools we use to construct the software layer, starting with EasyBuild, which is a framework for installing scientific software on HPC systems. It was originally created by HPCU Ghent in 2009 and has been public and stable since 2012. Software installed with EasyBuild is optimized for the processor architecture of the host by default, which is important in this context. It has support for almost 2,000 different software packages, not including extensions like Python packages or R libraries, or software versions. And it has support for several notorious packages when it comes to getting them properly installed, including OpenFOAM and TensorFlow when you're installing it from source. A large community has emerged around the project, and there have been various meetups and user meetings in the last couple of years, the last of which was organized together with HPC Now in Barcelona. Over the years, EasyBuild has received contributions from over 250 different people, and we have about 100 yearly contributors. For more information on EasyBuild, please look at the website and the documentation, or the recorded talks that we have in our YouTube channel. Next to EasyBuild, we'll also use LMOD in the software layer, which is a modern implementation of the Environment Modules tool, a well-known mechanism for managing your environment to access scientific software installations in an HPC context. It is implemented in Lua and developed by Robert McClay at the Texas Advanced Computing Center. LMOD has seen quick adoption in the HPC community in the recent years as a replacement for the more classic Tcl-based modules tool. It is compatible with module files both written in Tcl and Lua, and was designed specifically to provide support for hierarchical module trees, which may come in useful in the EESSI project. It provides lots of additional features as well, and it is a default modules tool in EasyBuild. Finally, we will also use the new ArchSpec library in the software layer, which is a library to reason about system architecture aspects. It was originally part of SPAC, which is a tool similar to EasyBuild, but it's now a standalone library. ArchSpec is currently focused on CPU microarchitectures, but the intention is to extend the concept to also network and GPUs and other aspects of the system. It consists of two parts. It includes a JSON file, which is a database with detailed information about CPU microarchitectures, covering Intel, AMD, ARM, and Power CPUs, and it provides human-readable labels corresponding to the code names of the different CPU microarchitectures, like Haswell, Skylake, Rome, and so on. In addition, it provides a Python library for leveraging this data and for reasoning about the information that it provides. It provides functionality to query the instruction set support of specific CPUs and to check the compatibility between multiple CPU microarchitectures. The project is a collaboration between myself and Todd Gamblin and Massimiliano Culpo, who are both SPAC developers. So what can we do with ArchSpec? It can collect host info. This is done through proc CPU info on Linux or the sysctl command on macOS. And it can use this information to determine the code name of the host CPU. It provides a small command line interface for doing this. If you run ArchSpec CPU, you will get an answer back like Skylake or Haswell. It can also check whether a given host is compatible with a particular microarchitecture. So you can ask it questions like, can my current host run binaries that were compiled for Intel Haswell? And you would get back a yes or a no. It can also be used to query the capabilities of microarchitectures and even to check for compiler flags that should be used to compile for the specific architecture. It also knows a partial ordering of microarchitectures, which means you can use it to pick the best match from a list of options. For example, if you have binaries for AVX, AVX2, and AVX512 architectures, you can ask it which of these should be used on an Intel Broadwell system. In the context of the EESSI project, we will use ArchSpec for two things. First, to obtain a label for a CPU microarchitecture, which we can use in the software installation prefix that we will use in EasyBuild. The example shows an example prefix for an Intel Haswell system. In addition, when using the software stack, ArchSpec can be leveraged to determine the best part of the software stack for the particular host. So for example, if your host CPU is an Intel Broadwell, and the software stack provides installations for AVX, AVX2, and AVX512 systems, ArchSpec can tell us that we should use the Haswell or the AVX2 installations on this Intel Broadwell system to obtain compatible installations while getting good performance. Another aspect of the EESSI project is testing of the software installations. Just getting the software installed is not enough. We also need to ensure it actually works and works well. So we want to be able to verify both the correctness and the performance of the installations we include in the software stack. For this, we plan to use Reframe, which is a software regression testing framework for HPC systems developed by CSCS. For end-user applications we include in the software stack, we want to also include test scripts, which we can use to verify both the correctness and the performance of the installations. For this, we hope to work closely together with the developers of the scientific software we include in our stack. Now let's take a look at the opportunities and the challenges we see in the EESSI project. We hope to provide a platform for collaboration across the HPC community, ranging from HPC centers, vendors, consultancy companies, and even the developers of scientific software themselves. We want to let users seamlessly hop between sites by providing the same software stack, no matter which system they are working on. We also want to allow people to leverage each other's work more efficiently when it comes to optimized scientific software installations, and to provide tested installations for the HPC community. We also want to facilitate benchmarking and make it easier to answer questions like, should I be using AVX2 or AVX512 binaries on my Skylake system, which is not that easy to answer. We also hope to work together with the developers of scientific software to vet the installations and to make sure that the installations we provide are not only correct, but also performing well. Of course, there are also many challenges in an ambitious project like this. We will need to find the time and manpower to get everything set up properly and to make sure it's working well. We'll need to correctly deal with network interconnects so we can get MPI software that is performing well, and how to leverage resources like accelerators and GPUs from the host. We will need to deal with a wide variety of CPU microarchitectures way beyond x86, including ARM and maybe even Power and RISC-V. We'll need to figure out how to deal with licensed software that we cannot just freely distribute in a shared software stack like this. This includes commercial software like the Intel tools, MATLAB, and ANSYS. We'll also need to check how we can correctly integrate with resource managers available on the host like Slurm, and whether we can still leverage vendor-provided software like the Cray programming environment provides. We will also need to come up with compelling arguments to convince site admins to adopt our software stack, because they may feel they are losing control. Finally, the answer to questions like, will X actually work in your approach? The answer is usually yes, because Compute Canada already did it. And this is something we can build on in this project. Let's take a quick look at the current status of the EESSI project. It's still very early stages, and we're mostly still working on getting a functioning pilot set up. We're having monthly online meetings to discuss our progress and the next steps we want to take. Up until now, we've already made good progress in all 3 layers of the EESSI project. We have an automated rollout of the CVMFS file system using Ansible already working, and we're actively testing with Gen 2 prefix. We have done an extensive brainstorm on how to design the software layer, but the actual work there has still to be started. We're also working on setting up documentation, a website, and organizing our work in GitHub repositories. With the pilot setup of the EESSI project, we want to work on figuring out our workflow and who will work on which aspects of the project. We hope to weed out roadblocks in our current plan and identify anything we've overlooked so far. And also we want to set up the first round of documentation on how to adapt to our software stack, how end users can leverage it, and so on. We're purposely sticking to a very limited scope in this pilot setup. So we're sticking to a small set of CPU architectures and maybe 1 or 2 types of GPUs. We'll stick to the default module naming scheme in EasyBuild for now. We'll focus only on Linux clients, so Mac OS and Windows is not something we're looking at right now. And we'll also stick to a small software stack of open source software, which includes OpenFOAM, TensorFlow, maybe GROMACS, and probably some bioinformatics pipeline. The pilot setup of the EESSI project is certainly not for production use, it's only for testing purposes, so keep that in mind. To wrap up, we want to ask for your help and feedback. If you're interested in the project, please reach out to us and let us know. We're currently looking for active contributors who can help out with setting up the pilot setup. We're mostly focused on European members of the HPC community right now, who are interested in joining our effort. If you have any experience with installing scientific software, with or without EasyBuild, and if you know about Git and GitHub, that's certainly helpful, but it's not a strict requirement. Of course, we also welcome suggestions for nice locations to have beers together. For more information on the EESSI project, you can visit our website, check out our GitHub repositories, take a look at our documentation, or follow us on Twitter. If you have any questions or feedback on this project, don't hesitate to send me an email. Thank you very much for your attention, and enjoy the rest of the conference.